level maths teaching. I'm David Forster. In this video of A-level exam revision, I continue to go through the Edexcel paper 1 from 2020, and this time I'm going to finish the paper with questions 14 to 16. Question 14 is a modelling question. A large spherical balloon is deflating. We have time t seconds, radius r, and volume v. The volume of the balloon is modelled as decreasing at a constant rate. Using this model, show that dr dt equals minus k over r squared. This sort of question has three related variables, here volume, radius, and time, and we need to use the chain rule to link them together. So we're given some information. We're told that the volume is decreasing at a constant rate. In other words, dv dt equals minus c. dv dt is the rate of increase. It's actually a decrease, so it must equal a negative number. So I've put it minus c, where c is a constant. We now need to bring in the radius, r. The relationship between volume and radius here, it's a sphere, is that v equals 4/3 pi r cubed, the volume of a sphere. So if we differentiate, we get dv dr equals 4 pi r squared. So using the chain rule, minus c equals 4 pi r squared times dr dt, which rearranges to dr dt equals minus c over 4 pi r squared. And we write c over 4 pi, it's a constant, as k, giving us the answer we require. Part B, we've been given some information: initial radius, radius after 5 seconds, and the volume continues to decrease until the balloon is empty. And we're asked to solve the differential equation to find a complete equation linking r and t. So taking our differential equation, we separate variables and integrate. R's to the left, t's to the right. The integral of r squared dr equals the integral of minus k dt. Integrate, a third r cubed equals minus kt plus c. We're told that when t is 0, r is 40. Substituting that in, we get c equals 40 cubed over 3. We're told that when t is 5, r is 20. Plugging that in, we get 20 cubed over 3 equals minus 5k plus 40 cubed over 3, which rearranges into k is 11,200 over 3. So, multiplying through by 3, we get r cubed equals minus 11,200t plus 64,000, or equivalent. The question doesn't ask us to find r as the subject. R cubed will do here. What we do want is exact numbers, not decimals, in these positions. Part C. This is the limit of the validity of the model. The limit we've got is, clearly t must be positive, greater than or equal to 0, but also we're told it continues to decrease until the balloon is empty. That is when r is 0. So let's plug in r is 0 and rearrange, and we get the time would be 40 over 7. So the limitation on time is that t is greater than or equal to 0 and less than or equal to 40 over 7, or if you like, 5.71 seconds to 3 significant figures. This is a fairly standard question on differential equations and modelling. Candidates found part C quite hard. I think possibly didn't understand what was meant by it. So a quick peek at the mark scheme. We get the comment here. Students found aspects of the question difficult, despite the fact the differential equation is not too demanding. Well, they're right. It's a very standard differential equation. Only high-scoring candidates made significant progress. Some candidates failed to use the chain rule. Common errors were not explaining how k over 4 pi is replaced by k if they were using k instead of c at the start, and using an incorrect formula for the volume of a sphere. In part B, candidates often separated variables correctly and integrated, but then did not handle the constants correctly and then could not apply the given conditions. Part C, many students were confused by the wording and did not realize a limiting value for t was required. Many candidates simply stated t could not be negative. Modelling is an important part of the mark scheme for A-level. It's got to be in the paper, no matter what board you are studying with. So it's worth practicing and being clear on the modelling parts of these questions. So, on to question 15. We're given here the equation of an implicit curve, x squared tan y equals 9, for y being between 0 and pi over 2. And we're asked to show that dy dx equals what it says here. Now, the best way of dealing with this is to differentiate implicitly. That is, go the whole way through using the product rule and differentiating with respect to x. So we're using u equals x squared and v equals tan of y. Du is 2x, dv is sec squared y, dy dx. The reason the dy dx is here is that we're differentiating tan of y with respect to x. So we do it with respect to y and get sec squared of y, and then we have to multiply it by dy dx. So the left-hand side differentiates to 2x tan y at x squared sec squared y dy dx, and the right-hand side differentiates easily to 0. Rearrangement: dy dx equals minus 2x tan y divided by x squared sec squared y. Now the question is written not in terms of x and y, but we're asked to find something with just x in it. On the top we have an x tan y. If it was an x squared tan y, we could replace it by 9. On the bottom we have a sec squared y. We don't really want sec squareds, we want tans. And that makes us think, what do we know about sec squared? Well, we should know two things about sec squared. The first thing is that tan differentiates to sec squared. And the second is there is a commonly used identity, which is that sec squared equals 1 plus tan squared. And that's precisely what we want in this question. So we replace sec squared by 1 plus tan squared y. I'm going to multiply the top and the bottom by x squared, because on the bottom that will give me x to the 4 plus x squared tan y squared. And I know x squared tan y is 9. So on the top I end up with minus 2x times 9. And on the bottom with x to the 4 plus 9 squared, which is minus 18x over x to the 4 plus 81 as required. Part B. Prove that C has a point of inflection at the fourth root of 27. Now we know points of inflection occur when d2y dx squared equals 0. We may need a little more than that as well, and we'll come back to that point. So I want to differentiate the expression for dy dx with respect to x, and the obvious approach is to use the quotient rule. So u is minus 18x, v is x to the 4 plus 81, du is minus 18, dv is 4x cubed. So putting those into the quotient rule formula, I get x to the 4 plus 81 times du minus 18, take away u dv minus 18x times 4x cubed. I've taken the minus 18 out of brackets, leaving me on the top with x to the 4 plus 81 minus 4x to the 4, which is minus 3x to the 4 plus 81. and that expression has got to equal 0. Rearranging, if an expression, a fraction, is naught, it's the top that's naught. So x to the 4 must equal 81 over 3 equals 27. X is the fourth root of 27. Now, many candidates would just stop there. You've got the answer, that's it. But what we've not actually done is shown that it's a point of inflection. We've shown that the second derivative is 0. It's not quite enough. Why not? Well, it's tempting to think that that's enough, but d2y dx squared is naught in itself doesn't prove a point of inflection. In rare circumstances, for example, y equals x to the 4, the second derivative would be 12x squared, which is naught, but it's actually a minimum turning point. One good way of showing that it is in fact a point of inflection is the sign change method. So just to say that when x is less than the fourth root of 27, the second derivative is less than naught. In other words, the gradient is decreasing. When x is greater than the fourth root of 27, the gradient is increasing. So it was decreasing to the left. It's naught. There's no change in the gradient at the point itself. And to the right, it's increasing. That is a point of inflection. And for the last mark, you're going to need to say something like that. Having a quick peek at the mark scheme. Fully correct solutions were very rare, but many candidates were able to score marks. The first 2 marks on implicit differentiation. Proceeding to the required result was a little more challenging, and only high-achieving students noticed that we could use 1 plus tan squared equals sec squared. So something worth noting. In part B, candidates often got an unsimplified second derivative. Where the first A was scored, it was usually for x equals the fourth root of 27. But very few candidates seemed aware they needed to show a change in sign of the second derivative to show a point of inflection. So something really to store away for next time. Okay, last question is a proof question. Prove by contradiction that there are no positive integers p and q such that 4p squared take q squared equals 25. Proof by contradiction means that you assume that integers p and q do exist and work with that and just show it doesn't work. Now, there are various ways you can approach questions like this. You might think odd numbers, even numbers, but in fact, the big clue here is the left-hand side is the difference of 2 squares. Be alert for those. In problem solving, differences of 2 squares are fairly common. So if we separate that left-hand side, we get 2p plus q times 2p minus q equals 25. Now, if p and q are positive integers, so are those 2 brackets. So we only have a limited number of options here. We could have 2p plus q equals 25 and 2p take q is 1. We could have both brackets to be 5. And maybe we could have the third option. The first is 1 and the second is 25. Though you will probably say straight away that can't be the case, because if p and q are positive, 2p plus q must be bigger than 2p minus q. For that matter, the second option can't be true because q would be naught, and that's not a positive integer. So back to option 1. If we add them together, we get 4p is 26, p is 6.5, and q would be 12. 6.5 is not an integer, so we rule out option 1. Option 2 we can probably rule out because q would have to be naught. P would also have to be 2.5, not an integer. And for option 3, we've already ruled it out, but if we worked out p, we would get 6.5, not an integer. There are 3 options and none of them work. So no other options, so no positive integers, p and q, that fit. Okay, A suggestion I would make is, for this type of proof and for problem solving, make sure you're familiar with equations in whole numbers where the options can be listed. So for example, if a times b equaled 12, where a and b were integers, you could list the options. A is 1, 2, 3, 4, 6, 12, maybe negative numbers, but there's only a limited number of options there. Make sure that's a tool in your armory for these proof questions and for problem solving. That's the end of this paper. Quite a tricky paper. Tricky papers are good for revision because all sorts of difficult points come out from which you can learn. And I hope you've learnt a lot from this paper. I hope you've learnt to work in the sweet spot, which is fine-tuned for you to get an A star without wasting time. That you've learned to shift perspective, thinking like a mathematician, so that even the hardest exam questions you will be able with practice to do correctly and confidently. And thirdly, exam secrets. Lots of secrets shared here, some of them from the exam mark scheme and some from my experience, and I hope you've learned from that. If you want further information about the sweet spot maths method, do send me an email on support@davidforster.org.uk and I'll get over to you some further information without any obligation. Thank you very much for participating in these lessons on the Edexcel Paper 1 from 2020.